The range is the easiest one to calculate. And that kind of makes it very appealing, right? Easy's good. But all we do is we find the highest score in the data set, so that would be the maximum score, and we subtract the lowest score in the data set. So that would just boil down to max minus min. Maximum score minus minimum score. Again, that's really easy to do unless you have like 20,000 numbers, and then you better hope you have a statistics program like SPSS to identify the highest and lowest score for you. But once you have these, it's a very just, quick subtraction. So it's super, super easy. But it's also very, very crude. And the reason why I'm saying it's very crude is because the range only sees two numbers. It only sees the highest score and the lowest score. Everything else it cannot see. So that's bad because it avoids what we call clumping or clustering. And I'm going to illustrate that for you. Okay, so for now, I want you to focus on just these blue bars. And let's pretend that these blue bars represent, I don't know, 1 million people. So 1 million people scored on a test between 49 and 52. Okay, so that represents 1 million people. So here we would say that there's not a lot of variability, right? 1 million people scored between 49 and 52, and about the same number of people got each score. So there's not a lot of variability here. And in fact, if we were to calculate the range, it would be 52 minus 49, and that gives us 3. So with a range of 3, we would say, wow, that's not very variable. We would say that these scores are clumped together, clustered together. In other words, there's not a lot of dispersion. If they're all clumped or clustered together, that means they're grouped, they're not dispersed. Now, let's pretend that my brother comes along, takes the test, and he gets a score of 5. Now, I had to put the bar high enough so you could see it, but in reality, that's just one person. So my brother comes along, gets a score of 5. What does this do to the data set? Well, to the data set, it's going to increase dispersion, right? Because now we see that 5 is very different from these other numbers, and so there's more dispersion. The numbers are more dispersed. But if we were to calculate the range and say, well, what does it do to the range? All of a sudden, we have 52 minus 5, and that is what, 47, right? So we've gone from 3 to 47, and it's all because of my little brother here getting a low score of 5. It just takes one person, in this case, one outlier, to suddenly explode the range. All right, should that one score really have increased the variability by that much from 3 to 47? I would say no, right? Let's look at what happens over here. You come along and you score 100. Now again, this just represents one person, okay? So because I have you scoring 100 and my brother scoring 5, in other words, now I've got 2 outliers and they happen to be in opposite directions, what is the range now? Well, now the range is 100 minus 5, so it's 95. All right, so should it be 95 when we have 1 million people getting between 49 and 52 and only 2 people out in the tails, right? We would call these tails. Really, should we say that there's that much variability? I would say no. It's misleading to say that the range is 95. I mean, it's not wrong to say the range is 95 because it is, but in terms of representing variability, it's doing a really poor job. And the reason why it's doing such a poor job is because the range does not see this clumping or clustering. It's as if it's not there. The range only sees 2 numbers, the lowest and the highest. So really, we don't want to use the range because it's so insensitive if we have clumping. If we have clumping or clustering, we don't want to use the range. So what effect do outliers have on the range? What do? They increase the range, right? So by adding the 5, it exploded the range. By adding 100, it exploded the range even more because now we've got 2 outliers. So outliers, if they're present, you should not use the range. Now think about this one. What effect does clumping have on the range? Think about it. You should say nothing. It has no effect. Why does clumping have no effect? Because the range doesn't see it. The range doesn't, it's as if this doesn't exist. It sees this number and this number, that's it. So the clumping has no effect on the range. Now, what you should be doing is plotting your data, get a frequency distribution. And if you see clumping or clustering, don't use the range. All right? Because again, the range won't see it. All right? So never use the range without checking for clumping or clustering first. Get your frequency distribution and decide or look at it and see whether or not there's any kind of clumping or clustering. And again, if there's not, if the numbers are all evenly spread out, evenly dispersed between 5 and 100, then okay, you can use the range, no problem. But otherwise, stay away from the range. Now, there is another reason why you should stay away from the range, and that is the range is overly dependent on sample size, which means that depending on whether we have big samples, medium-sized samples, small samples, we're going to get very different estimates for range. And that shouldn't be the case. The estimate of variability ideally shouldn't be so dependent on the size of our sample. So I'm going to give you an analogy first, okay, and then we'll talk about range. So let's pretend we've got this, jar of jelly beans. And let's say that unlike this jar that has many different colors, our jar of jelly beans has only 3 colors. And let's say that 500 are red, 300 are blue, and maybe 10 are white. Okay, so 500 are red. What did I say? 200 or 300 are blue, and we've only got a handful of white. If you were to ask little Harry Potter, okay, so the Harry Potter, when he was really, really young, if you asked him, to come into the room, blindfold him, and reach in and pull out a handful of jelly beans, well, which ones is he most likely to get in his hand? Well, he's got really, really small hands, right? So you would expect him to have mostly red, because red was the most frequent color. So most of the jelly beans would be red. But you would also expect some blue because there were still quite a few blues, right? But what you wouldn't expect, if there's only like maybe 10 white jelly beans, you're not going to expect a lot of those in his hand, if any. In fact, with only 10, I would say, no, I doubt he's going to have any of those 10. Those 10, after all, are the outliers, right? And if he reaches in and is only able to grab a small handful, then good luck getting the white. But then along comes Hagrid. And Hagrid, in comparison to Harry, has huge hands. So if you blindfold him and ask him to reach into this jar of jelly beans, he's still going to pull out a majority of his handful will be the red jelly beans. Because again, that's the most frequent color. So if he's just reaching in at random, we would expect red to be the most frequent. in his hand. And then we would expect blue to be next because that's the most frequent color. Now the question is, would he likely get any outliers, any of the white jelly beans? Well, if you look at the size of Hagrid's hands and the size of the jelly bean jar, then yes, there's actually a good chance that even though the white jelly beans are not very common, with such a huge sample size, we would expect him to pull out some white jelly beans. Okay, so now let's relate this to sample size and the range. Okay, so if we look over here, we have a distribution that is normally distributed. Now here I show a perfect normal distribution. Our distribution won't be quite this perfect, but it resembles this shape. All right, now if we take a small sample from this distribution, well, that means that with a small sample size, what are we most likely to get? Well, scores that are from the middle of this distribution, and that's because these are the most frequent scores, which means they are the ones that are the most likely, right? In a sample, you get the scores that are the most frequent. So if we were to calculate max minus min, then we would see that the range is a very small number, okay? And it's because we're getting the most frequent scores with a very small sample. You probably won't get any outliers. But what if you do take a larger sample? What if you get Hagrid to do your sampling for you? Well, it's still going to be the case that most of the numbers in your sample are going to be from the middle of the distribution, the more frequent numbers, right? But if you've got Hagrid doing your sample, then sampling procedure with his large hands, he is likely to pick up outliers. So he may pick up an outlier in this tail, an outlier in that tail. Maybe he's only going to get outliers in one tail. But regardless, as soon as you have outliers, what does that do to the range? Well, when you do max minus min, all of a sudden you're going to get a much larger range. So what this is telling us is that even though the distribution itself doesn't change, your data set's not changing from up here to down there. It's the same data set. But just by changing your sample size, you can dramatically increase the range. And so that's what we're seeing. The range is overly dependent on sample size. It may overestimate the size or the amount of variability you have. And again, it's because the range doesn't see any of this clumping or clustering. It only sees the biggest and the smallest number. So for those reasons, for the most part, we stay away from the range. Sometimes you see it reported, but not very often.